Alrighty, folks, let's begin. Last lesson, or last lecture, I should say, what we were looking at is adding a categorical variable to our regression model. So we looked at, well, what happens if this categorical variable only had two levels? So we introduced a dummy variable, where the dummy variable only takes 0 or 1. So 0 representing what our first level is going to be, 1 representing what our second level is going to be. And the main thing that we saw with this is if the data supports having this dummy variable in there, what we should see is when we graph the data, so if we do a scatter plot and we color the points for the different levels and we did a line of best fit, these two lines should have relatively the same slope. It may not be perfect because, again, we are grabbing a sample. In theory, it should be exactly the same slope. But again, in practice, what we should see is there's probably going to be a slight difference. But the main part of this is we should see a different intercept. So that's the key part. So going from level 0 or level 1 to level 2 of our categorical variable, I should say, maybe not going up, maybe sometimes it's going down, our intercept changes by that beta 2 variable. Okay, so now the question becomes, well, what happens if there is more than two levels? Well, we can't simply just use the one dummy variable that we have because, again, it can only take 0 or 1, which represents, again, level 0 or level 1 of our categorical variable and level 2 of our categorical variable. So what do we need to do? Now, one thing to note is when we had two levels, we only needed one additional variable in terms of our model. Now, when we get to this, what we're actually going to need and what we're going to see in just a second is we only need two. So it's always going to be the number of levels we have minus 1. So if there's k levels, and this is exactly what I have down here. So if I have k levels, oops, I don't want this. I want my pen red. Okay. If I have k levels, I'm always going to need k minus 1. Whoops. Why is this? There we go. That should be written underneath. K minus 1 dummy variables. So this time around, let's consider having three levels, and we'll call those levels A, B, and C. Since, again, the dummy variable can only take 0 or 1, we need to add two dummy variables into our model. So let's call this, and we're going to order the levels. The first level will be A, the second level will be B, and the third level will be C. So I'm going to add in exactly the same way we did beforehand. We added in not the first level, but the second level into our model. So what we're going to do is we're going to add not the first, but we're going to add the second and the third. So we're going to say D sub B, we're going to add, and D sub C. So our model is y is equal to beta naught, that's going to be our intercept, plus beta 1 x1, x1 again being our numerical variable, plus beta 2, which is our scalar for our dB, and beta 3, which is a scalar for dC. Okay, same as before when these things are 0. Because remember, it's a categorical variable. We can only be on one level at a time. So when we are on that very first level, the two parameters that we've just added in here, the two variables that we have just added in here, will need to be 0. So that's going to represent level A. So that's why we say we always need that k minus 1, or that 1 less than the number of levels that we have, because when all the variables are shut off, or 0 is put into them, or false, however you want to look at that, that is our very first level. And then once we activate them, that change, that activation, and we're only activating, again, one at a time. Once we activate them, then that increase or decrease on the intercept is what we get when we transition from that first level to whatever level that we are in fact going on. Now I'm going to repeat that part because that part is important. There is always that reference level, and in this case we're considering it that very first level, so that's A. So if I activate or I turn on or add 1 to, not add 1, but I put a 1 in the D sub B, that's the difference from going from A to B. And same as if I do the D sub C, if I put a 1 in there, but again, the D sub B will have a 0 because only one level at a time. If I do a 1 in the D sub C, that's the difference going from level A, the reference level, up to, or maybe down, again, depending on what the scalar beta 3 is going to be. That's going to be our change from the reference level, or the first level, or in this case A, to whatever C is going to be. So we're not talking about the difference between B and C. It's always talking about from our reference level, or our very first level. So if we decide to order it, whatever the order is, the very first being our reference level, again, what is the difference from that? All right, so we said when both of those are equal to 0, we get level A. When d sub b is 1, we get a level B. D sub c is 1, we get C, and again 0 for otherwise, or 0 for everything else. So how will this look? Well, it's going to look exactly the same, or the idea of it's going to look exactly the same when we had 2 levels. So when we had 2 levels, we had the same slope, or ideally the same slope, different intercept. That's exactly what we're looking for again here. So when I plug in for my 2 dummy variables, both 0, again, I'm on level A. So what do I end up with? Well, it doesn't matter what beta 2 is going to be. It doesn't matter what beta 3 is going to be because I'm multiplying that by 0. They disappear. So what I'm left with is my beta naught. So my starting point for my level A plus my beta 1 x1, which is again how it changes when I increase my numerical variable. That's going to be my slope. So this is it. For level B, again, the second dummy variable, the second dummy variable is going to be set to 0. That's my d sub c. A 1 is going into my d sub b. So this term, this very last term disappears. This one is going to stay. Beta 2 times 1, well, that's just going to be beta 2. Again, combining like terms, we have beta naught plus beta 1. So again, the change starting at our reference level, beta naught, our change is beta 2, how we go from reference level or level 1 to level 2, and then slope stays the same. So again, same slope, different intercept, and you guessed it, same idea for part C. Beta 2 is going to disappear because I'm multiplying it by 0. Beta 1 or beta 3 times 1 is just beta 3. Combine my like terms. I have my reference level, beta naught, my increase or decrease depending on the sign, bringing me up to level C. So that's my beta 3. And again, same slope. So I would look at this as something along the lines. And let's change up colors because I know we can do this now. Let's go to a black line. So this might be for A. We'll do yellow now. This might be for level B. Ooh, I don't really like that one. Can't really see that one. But we'll stick with it. B. Sorry about that. Note to self, never use yellow. It does not work all that well here. Or maybe you can see it nicer on the screen than I can. But yeah, that doesn't look like that's all that nice. See, we learn as we go. Do not use yellow in presentations. And we'll say this is C. Assuming those are all same slope and I've drew those nicely, they're not quite there, but live in hope. So this would be if B was positive and C was negative, or I should say if beta 2 was positive and beta 3 was negative. So this would be my drop from A to C. This would be the difference of beta 3, and this is the difference of beta 2. So again, it's all starting from our reference level. That's our black line. That is A. That's our very first level. And as we saw in the last class, we can order inside of R how we want those levels to look. So if we wanted the line on the very bottom, if we wanted that to be the reference level, I can reorder things in that order. So all of my betas are forcing them to be positive. But again, if you're remembering that it's always from that reference level, well, then you can let R just do it automatically, but it will do it alphabetically. All right, so let's jump back to the example that we were playing around with last class. So again, this is our electronics store. Our numerical variable here, or I shouldn't say our numerical variable, our reference response, there we go. Not enough caffeine yet today. Our response variable, our Y, is going to be sales. This is what we are looking to predict. Our numerical variable is our household, so that would represent our X1, or households within a given region. Our categorical variable is location. So before we were starting with street and mall, now we're adding in downtown. And if you remember when we pulled in the data for this problem, we had all 3 different locations. We filtered out to get rid of downtown for our last example. Now we want to include that back in. All right, so let's jump back to R. Here we go. Still having everything up here. So I'm going to create a new variable called 3level. I'm going to take the variable dummy, which has the original data that we brought in, and I'm just going to rename that, or I'm going to take whatever's in dummy, I'm going to put it inside of the 3level. There we go. So 3 level looks like this. It's got the 15 observations. Everything is there as it did beforehand. So it has the location, street, mall, and downtown. So the question then becomes, and I don't know if I have the question up here. Oh, I do. Perfect. So it says, in addition to the data from exercise 1 concerning street and mall locations, they have also collected data concerning a downtown location. We want to plot the data and discuss why the data plots indicate the model. So this is what we were looking at before, that y is equal to beta naught plus beta 1 x1. Now we want to add in the two categorical variables, the beta 2 d sub m plus the beta 3 d sub d. Sorry, yeah, because we're labeling it the mall and downtown. So it's already told us the order of the categorical variables based upon the subscripts that we have here. So the second level would be mall, the third level would be downtown. That means street is going to be the first level. So I want to make sure, because I know when I put this into R, if I just said, let's turn this this categorical variable, or sorry, let's change this character variable into a categorical variable, it's going to order things alphabetically. We want it as street comes first, mall comes second, downtown comes third, based upon the data that we have here. All right, so first things first, before I even do that, let's plot and see if it actually makes sense. So that was what we did last time. We wanted to plot the data, so we do a scatter plot. On top of that scatter plot, we color our dots based upon the level of the categorical variable, and then we do a line of best fit. Do we have those three parallel lines with different intercepts? So using ggplot, we'll do this. So again, that very first level, or the very first layer of ggplot, is the data that we're using. So that's the 3-level data frame. The second is the aesthetics, how we are mapping the parts of our graph to the data set that we have. So we're saying the x-axis represents households, the y-axis represents sales, and again, we want to color based upon location. The third layer is that geometry. How do we want our points to look? In this case, we want them as points. And last but not least, the geom_smooth will do a line of best fit. So the method that we want to use here is the linear model. So we want the lines of best fit, and we want that standard error to be turned off, because I don't care about those grayed areas in there. What we were just looking at is, how do the lines look? Are they parallel with different intercepts? Awesome, we're good to go. Okay, so let's Control Enter to execute this. And now let's talk for a second where there may be potential problems. So we know that the green line, which represents mall, the blue line, which represents streets, these are perfectly fine. We've run the hypothesis test. We've shown that there is a difference, a significant difference between this, or a statistically significant difference at alpha being 0.05. Yeah, 5%. But now what we've added in is this red line here, which represents downtown. Now, if we look at the difference between the red and the green, so downtown and mall, both of these lines look relatively parallel. They also kind of look like they might converge up at the top here. So we don't know what long-term this is going to be. But again, we know it's not going to be perfect because we're taking a sample. So the slopes are not going to be perfectly the same, even though in our model, theoretically, they are exactly the same. We've taken a sample here. We're not expecting it to be absolutely perfect. So they look relatively good here, and there looks to be a difference. We already know from green to blue, that's perfectly fine. But now let's look at red to blue. Slopes, again, same idea, might converge a little bit later on. But again, perfectly fine. But what problem might we see? And you can take a second, pause if you want. Let's think about this. What potential problem could we run into? No, I didn't just freeze. I gave you a second there to pause. Look at the difference between those two lines in terms of intercept. Very, very small. This could be problematic. We may see that there is a difference between these two things based upon the sample that we took. But because they are so small, even in here, statistically it might not be significant enough. So adding in that downtown, does it really change anything? Or could I already model this just using mall and street? So that's a good question. This is why we need to run through that hypothesis test, because it does look like there is a difference, but that difference is incredibly small. So we need to check whether or not that is statistically significant. And we're not able to do that just based upon the picture. We have to do that based upon the test that we do here. Okay. So that is our first part. So we have an idea that yes, it could potentially fit this model. We do have three lines. They do look parallel to one another, not perpendicular, parallel to one another. So same slope, different intercept. So perfectly valid to consider the model that we have right now. But again, that's that difference, that adding in downtown. Maybe street was enough. Maybe street and mall was really everything that we needed to know, and we can combine street and downtown, that there's no difference between the two, or we can leave them in there if there's a valid reason for wanting to leave them in there. All right, so let's run through the hypothesis test now. So what we're going to do is, again, we are going to change that variable, because if I look at up in my global environments here, or you can run the str, that structure function on the data frame, what you're going to see is exactly the same. So notice again, location is a character vector. I want to change this to a categorical variable, so I need to run it through the factor function. So I'm changing the location column of that third level data set. So I'm putting that through that exact same vector, or that column. I'm putting it through the factor function, but I'm also using the second argument, or the second parameter of my function, which is that levels, and I'm forcing how I want the levels to be ordered. So street comes first, mall comes second, downtown comes third, which is exactly the order I have this vector in. Again, I'm putting in a vector, and how do I create that vector? I use that C function. So C is for combine. I'm combining the elements inside of here. So I'm combining street, mall, downtown. So that's going to give me a vector with street first, mall second, downtown third. All right, so if I run line 52, notice in my top right, again, under that global environments, the location is now a factor with three levels. Those levels are street, mall, and downtown. So it's showing me that it is, in fact, ordered correctly. So let's build the model. I'm going to call this model 1. So I'm going to put inside model 1, I'm running the LM function, so that's our linear model function. That first input is sales. Sales is explained by households and location. So notice there is no difference than what we had beforehand. It's the exact same formula, even though there are multiple levels. So R already knows it's going to be a categorical variable with multiple levels, so it's going to put in those dummy variables for us. It's going to put in, it knows it has three levels, so it's going to put in those two additional dummy variables. And based upon how we ordered the dummy variables, ordered the categorical variable with being street, mall, and downtown, it's going to show up in exactly the same way we have originally dealt with our model. So that's our beta 2 is equal to D sub M, and our beta 3 is multiplied by D sub, I think I said equals to. That's not the case. Our beta 2 is linked with, or is our scalar for D sub M, and our beta 3 is our scalar for D sub D for downtown. There we go. Again, it's always that hard part. It's like, did I say that correctly? And I'm not going to stop and rewind and check and blah, blah, blah from there, because where's the fun in that? But if we were in class, someone would be able to correct me on this. So, boo to not being in class. But normally we do this as like a 3-hour lecture series. And for the history of doing this, sitting through this for 3 hours, I'm kind of happy that you don't have to do it. You could pause, take breaks, those sort of things. The 3-hour, hard for me. I can only imagine how difficult it would be for you folks to get through it. I remember being a student. There is no way I'm making it through 3 hours and paying attention to absolutely everything. I don't even want to hear myself talk for 3 hours. Who am I kidding? Of course I do. All right, so let's put this through. So sales explained by households plus location, data equals level 3. Let's run this through. And now we're going to do a summary. It's going to give us our output, which we can see down in the console here. All right, so our estimate, so this is my B naught, this is my estimate for beta naught, is 14.97769. My estimate for my beta 1, so this is my slope, is 0.86859. So it's not exactly the same because we have more data inside of here. And again, it's taking into account the 3 lines and not just the 2. Location mall 28.37376. So that is our estimate. That's our B2, our estimate for beta 2. And this is our B3, our estimate for beta 3, which is 6.68378. So if I look at my graph, again, that first line at the very bottom, that's my blue line. This is going to be my reference point. This is my starting at level A. So notice going from blue to red, where red is being the downtown, this jump here between the two, that is my that's my beta 3, because it's representing going from A to, or level 1 to level 3. So very small jump, that's my 6.86. Okay, so it is showing that there is a difference between the two, but again, we have to ask the question, is it statistically significant? Because it estimates that there is a difference between the two. Remember the fact that if I do a confidence interval, it may actually contain 0. So there might actually be nothing in there. So it's showing that, but if I want to be 95% confident where that true difference lies, 0 might be a possible option. If that's the case, it will definitely fail the hypothesis test. All right, so going from blue to all the way up to green, which is mall. So we've already kind of seen this in here, but based upon a different slope, we're going to expect a different intercept, a slightly different intercept. So going from street to mall, what is the difference between those two lines? That is my beta 2. My estimate for beta 2 is 28.37376. Okay, so that is the jump from going from here to here. So that's the increase in annual sales for a given month. I think this is for July. So we are roughly 28,000 and change more if we go from street to the mall location. We are roughly almost 7,000 more if we go from a street to a downtown location. But again, is that actually valid? Well, let's look at the confidence interval first, and then we'll run a quick hypothesis test here. So again, I want a 95% confidence interval. I want to do this for everything in Model 1. All right, so notice for my location mall, my confidence interval, so this is this part here, my confidence interval for my beta 2, so this is the going from level 1, or going from the street location to the mall location, I know my estimate, again, is 28.37376. Where does the true value lie? Where does my beta 2 actually live with 95% confidence? It's somewhere in the 18.554864 all the way up to 38.1930257. So we've taken that estimate, we've gone to the left, we've gone to the right, and we've said, well, the true value is somewhere inside of here. So both of those are positive. Awesome. Now let's look at, well, what happens if we went to street to downtown? Again, that was only a jump of almost 7,000. Well, here our lower bound is negative 3.6359712. Our upper bound is 17.3635248. Oh no, we crossed over 0. So it is possible that the true population parameter for beta 3, that increase or decrease going from a street location to the downtown location, could be 0. Okay, problematic. So let's do the hypothesis test. Now, I'm not going to do the hypothesis test for beta 2 because we already can see from here that there is going to be a difference, and we've already ran that the last time around. So we're only going to do it for beta 3 in this case. And hopefully you should be able to see it up at the top. I'm just going to use the little block that I have here. So our H naught, let's actually go here, eraser. Let's go with black. H naught, we're saying beta 3 is equal to 0. So that is our null hypothesis. We're simply saying that no, there is no difference going from level 1 to level 3 in this case, or to the street location to the downtown location. Versus the alternative, beta 3 is not equal to 0. And again, we're doing a two-tailed test because I don't care if it's positive or if it's negative. It could be an increase, it could be a decrease. I don't care. There is a difference. I'm just saying it's not equal to 0. Okay, so I need more information here. Let's go back to my R. Let's scroll up a bit. Here we go. So I'm looking at this very last line here. So it gives me a t-value. And again, if I want to find that critical value based upon the degrees of freedom and everything else that's going to be in there, I could do that. But for now, it's just so much easier to use the p-value and say if this is less than our alpha. And again, our alpha is 0.05. So we're dealing with a 5% error or type 1 error. Our p-value is 0.178. So notice that p-value 0.178 is actually greater than 0.05, which is equal to alpha. Therefore, we fail to reject. So if the probability of this happening is less than what our type 1 error or the amount we're willing to give for a type 1 error, so we're willing to risk 5% of the time making a mistake, if the probability of this happening is less than 5%, then okay, we're going to reject the null hypothesis, we're going to accept the alternative. But in this case, that p-value is 17.8%. That's a lot higher than 5%. So the probability of this actually being, or the probability of this, given the fact that the null hypothesis is true, yeah, we're going to fail to reject. So we fail to reject H naught at a significance level of 0.05. Again, we always have to include that level of significance. So for us, this is showing us that there really isn't a difference, or there is not a statistical significant difference going from that first level all the way up to the third level. So our reference level starting with, in this case, street location, to the downtown location, which is kind of what we saw, and that's why we paused for a second, or where I paused for a second. Hopefully you paused too to think about this one. But where we paused to say, well, those lines are very close. There is still a difference in the picture, but was that just because of the sample that we took? Now, maybe, here's the thing, maybe there is a difference, but we only grabbed 5 locations. So all we're saying here is we're not saying that the null hypothesis is true. We're not saying that it is 0. We just don't have enough information or enough evidence to suggest it's not 0. So if we gathered more evidence, well, maybe if we did more than 5 locations, maybe there would be a clear difference, and we would statistically say, yes, now at this point in time, there is a difference between the two. It just wasn't a random sample that we grabbed where it's demonstrated that there is something, as we have in this picture, but there is actually. We would need more data to be able to show that. At this point in time, we don't have that. We failed to reject the null hypothesis. I don't even need to do the confidence interval at this point in time. We did in advance anyways. I'm pointing over here because here's my screen. It's actually over here. There we go. My camera's a little bit of an angle. Perfect. It is right over here. Ish. There it is. But again, we don't really need it because the interval contains 0, which means the true population parameter could in fact be 0, which is why we failed over here. Okay, perfect. So that includes everything in terms of really the dummy variables, because everything else is just an extension of this. So what would we expect to see if I had more levels? Well, again, starting from my reference point, when all of my dummy variables are set to 0, once I turn on one of the different levels, that is my jump from my reference level to whatever level that we are going to. And that's just adding on that dummy variable for that level of increase. So again, if we have k levels, k minus 1 dummy variables are going to be needed. We treat them all exactly the same, and when we plot these, it's just a different intercept, same slope. Cool. Let's go back to my slides. Where's my mouse? Here's my mouse. Perfect. I wonder how many times through all these videos I'm like, where's my mouse? It's disappeared somewhere. Okay, too many screens. I've got a screen here, got a screen here, got a tablet here. Oh, too many things on the go. What am I looking to do now? Let's look at interactions. Okay, so we've seen that if I add on different levels, I add in different slopes. Again, if I color all of my dots or my points on a scatter plot based upon the or levels of the categorical variable, do a line of best fit, I should see different intercepts, same slopes. So let's take this up a notch and let's say what happens if there is an interaction between our numerical variable and our categorical variable. So we're looking at now interaction models. So far we have only considered dummy variables as standalone variables, so they don't interact in any way with the numerical variable is basically what I'm saying here. So however, we can also look at interactions between the dummy variables and other variables, as I've already said. So we're going to look at an easy example of just the dummy variable and our numerical variable, and what should we expect to see if we graph these types of things. So for example, when we only have two levels, and we'll stick with the two levels examples, because again, this extends all the way up to, doesn't matter, k levels. We're still going to have the k-1 dummy variables, but again, that interaction. So let's say our dummy variable, which is x2, we'll call it d, again, only takes the values 0 or 1. Let's go back to red. I like red here better than black. So our model by default, again, when we only have that 1, would be our y is equal to our beta naught plus beta 1 x1 plus beta 2 d. There we go. Because two levels means one dummy variable. A possible interaction model would look as follows. Y is equal to beta naught, beta 1 x1, beta 2 d, so exactly the same as we had before. Now we're going to add on an interaction term. Now remember, d takes the value 0 or 1. So if d takes the value of 0, multiplying it by anything else just automatically disappears. When it's equal to 1, well, now we have things that are not going to disappear. So our last term that we're adding on is a beta 3 times x1, so that numerical variable times d. Excellent. So what would this look like? We've seen when there's no interaction, what we have is same slope, different intercept. Well, what about this time around? So let's plug in the values for d. D can be 0 or 1, that's it. So this is our model, no change from what I had just before. That was the same as my last screen, my beta naught plus beta 1 x1, beta 2 d, beta 3 x1 d. This is my interaction term. So when I plug in 0, what am I going to get? Well, everything with a d is going to disappear. So that is my third and fourth term, and I'm left with my original model. This is my beta naught, beta 1, x1. Okay, just my line. I know, don't use yellow. Thank you for reminding me. So let's say this is my level 1. Okay, let's go back to my colors. Let's do red here for a second. When d is equal to 1, that means all of those terms do not disappear. So we know that third term, beta 2d, is just going to be beta 2. That's going to be the change in my intercept. So notice that I have my beta naught plus beta 2. So same as what we had before. So I should be able to graph things with different intercepts. But notice here, there is also that fourth term. So when d is equal to 1, what are we left with? Well, we're not left with just beta 3. We're left with beta 3 times x1. So I have an x1 here and x1 here. If I group my like terms, adding my coefficients together, I'm getting my beta 1 plus beta 3. So my slope is also going to change. It could increase, it could decrease, depending on, again, the sign of beta 3. But now I'm not only going to have a change in intercept, I'm going to have a change in slope. So if I do plot these things, and I do notice, well, wait a second here, my lines are not parallel. I do have different intercepts. I do have different slopes. Maybe there's an interaction term I want to add in here. So I need to take that into consideration. So if I'm looking at things and I see, okay, I have the same slopes, different intercepts, then I can think to myself, well, maybe the categorical variable is standalone. It does not depend on what's happening with my numerical variable. But if I have a different slope and a significant different slope, because again, we've seen slight variations there where everything works out, but if I see a difference in slope and difference of intercept, I might think to myself, wait a second, there is a possible interaction between my categorical variable and my numerical variable inside of here. Again, I'm only talking about these two things because this example only has one categorical variable and one numerical variable. All right, so things to note, with an interaction term, both the intercept and the slope are shifted, so they're different. All right, so let's work through an exercise here. What do we want to do in this case? We want to add the independent variable x sub dm. So again, we're only going back to our two levels. So we're going to look at street and we're going to look at mall. We're going to forget downtown even existed. So because I only have the two levels, I have an x dm. So the x again is my numerical variable. Dm is my dummy variable there. So we're going to add that term to our model from exercise 1, and we want to determine whether or not the variable is significant. What do your results imply? Okay, so what is our model? Our model is, let's go back and do black here. So y is equal to, we have a beta naught plus beta 1 x plus beta 2 d sub m. So that was our original model back from exercise 1. So we had, again, the second term being our numerical variable, the third term being our categorical variable, or a different level of the categorical variable. And now we're going to add on a beta 3 xdm. So we've tested this part here and we saw that it was in fact significant. So what we want to do now is we want to test something else. We're going to run this hypothesis test and we're going to say our null hypothesis is beta 3 is equal to 0 versus the alternative, beta 3 is not equal to 0. So if it's equal to 0, there is no interaction. If it's not equal to 0, there is some kind of interaction. We don't know what kind of interaction yet, but there's some kind of interaction that's happening here. Okay, let's jump over to R. So the first thing that we want to do, and same as before, let's build a scatter plot. Now this is the same scatter plot that we had beforehand. Now I said before that these two lines are not perfectly parallel. Okay, maybe there is an interaction. They look pretty close to parallel, but maybe not. So we know there is a difference. We know in our original model it works out. There is a difference. We should definitely add that categorical variable in there. But what about that interaction term? So they have a different intercept. They potentially have a different slope. But is it statistically significant? That is the key part. So that alpha being 0.05, that is what we are testing on here. So again, up at the top you'll see here, so alpha 0.05. There we go. So let's build our interaction model. And we're going to build this in exactly the same way we did in designs of experiments. So we're going to call this int model. I'm assigning to that based upon this linear model function. Sales is explained by households times location. So whenever there's an interaction, again, we'd use that multiplication. I can do households plus location plus households colon location to do that interaction, or I can just use the multiplication. Again, same thing as in the designs of experiments. I like doing the shorter version of this, so let's just keep this as multiplication. Data is coming from two levels, or two level, and run a summary on this. And before the summary, or sorry, before the confidence interval, let's run this test. Oops, what am I doing? My hand's on the keyboard. Don't do that. Too many zeros. Perfect. All right, so let's look at the output here down in the console. Where's my mouse? Here's my mouse. All right, so again, our estimate for beta naught, 7.9 and change. Our estimate for the slope is 0.92 and change. Our estimate for beta 2 is 42.7294 or 974. And last but not least, our change in slope based upon that interaction, and this is going to be a negative, so we're seeing a decrease in the slope, is negative 0.09172. So not a big jump, it's a very small one, and that number is very, very close to 0. So that might become problematic, because again, if I have to go a little bit to the left, a little bit to the right, chances are it's going to cross over 0, so the true population parameter could in fact be 0 for beta 3. All right, so we're going to grab the p-value of this. Again, we have the t-value that it already gives us, but then I need to find the critical value. I can simply use the p-value, same as before. The outcome is always going to be exactly the same. So my p-value is equal to, in this case, 0.58 0.8627. So what is this telling us? Under the assumption that the null hypothesis is true, that the true population parameter for beta 3, that change in slope based upon an interaction, assuming that it is in fact 0, if I were to run this experiment or collect the data, how often should I find that I'm going to get a slope of this type of a difference? And I should see this almost 60% of the time, 58.8627% of the time. That's really high. So what does that tell us? It means this random sample, I should see this slight variation a lot of the times here. It means I'm going to fail to reject this as a perfectly normal sort of thing to have happened. And again, we kind of got that general idea because the lines, there is a difference, but not a huge difference. And that's kind of the key part here. So because this, and again, if the probability of us seeing this, given that the true value is going to be 0, if that was less than 5% or whatever our significance level was, we could reject the null hypothesis. But we see this almost 60% of the time. So again, if I ran this experiment over and over and over again, 60% of the time, I should end up seeing a slope of this type of difference. So this is greater than 0.05, which is my alpha. Therefore, we fail to reject H naught. And if I were to run our confidence interval, I'm going to see a 0 as a possible outcome for my beta 3. And again, I'm doing that here by my last line. So this is line 71. Executing line 71, what do we see? For that interaction term, so households, location, mol, I'm getting that it's going to be negative 0.4846388 all the way up to positive 0.3012054. So there we go. Doesn't really help us. Okay, what else? So that's our beta 3. And also, how often should we see the location mol again? We have a p-value that's always incredibly high. So what this is telling us overall is this model, at least the interaction model, doesn't make sense. So we've already tested whether or not the model with 2 dummy variables makes sense. Awesome. Keep that one. But now our interaction model didn't pass the test. So, so that's it. When we're adding in dummy variables or categorical variables, again, what do we expect to see? This is the type of things that we would expect to see. Okay. What are we moving on to? What time are we at? We're still good. So let's look at one last thing here, and then we'll call this, this lesson. So this is all part of lesson 3, the first part of this this module. This will be done at this point in time. So let's go back to the slides. All right, so now we want to talk about using squared and interaction variables. Actually, this one might take a little bit of time. So let's pause this here, and then we'll come back to this one. Yeah, so this looks like a good place to stop for now. So we'll leave this be for here. We'll do one more lesson that'll complete one more lecture will complete lesson number 3, or sorry, lesson number 3 of module 2. And then we should be able to do 2 more lectures to complete the rest of this module. So we have a lesson 4 and a lesson 5. That sounds good. All right, we'll see you back here the next time. Thanks for sticking around. And again, if you've made it this far, reach out, send an email. Just say, hey, I made it to this point in time. I'm watching along. Thank you for watching along. We'll see you back here. Where's my mouse again?